referring to the most recent EIA data, we get about 85% of our energy burning stuff, typically stuff that has carbon in it. That includes the nice, highly condensed fossil fuels that have been placed in the ground for us over millions of years, oil, gas, and coal. In addition, we burn biomass, we burn biofuels, we burn waste wood, and so on, all of which, in every case, carbon in there unites with oxygen, makes carbon dioxide, goes into the atmosphere. There's usually hydrogen also. Hydrogen unites with oxygen, makes water vapor. And that's what happens when you burn things. Coal and oil have a lot of carbon, so they make a great deal of carbon dioxide when you burn them. Natural gas has a lot of hydrogen atoms. Methane is CH4. So burning natural gas creates water vapor as well as carbon dioxide. And so it produces less carbon dioxide per BTU of energy produced than those other fossil fuels. And that's why our push now to replace coal is mainly going to natural gas. In addition to that, natural gas doesn't have things like mercury and sulfur in there, which is a big problem from coal burning. The other 15% is mostly nuclear energy, which is about 8.5%. Hydroelectric is about 3%. And renewables like solar and wind are the fastest growing energy supply we have, but it's only about 1% of our total energy. So for the near future, we probably can't expect a lot from that particular source. As a result of all this burning, we have some problems. We're aware of the fiscal cliff that everybody's talking about, but we've got some energy and climate cliffs that are probably worse than the fiscal cliff. One school says that we're going to all freeze to death because peak oil and peak coal and peak whatever, we're going to run out of fuels. We'll be back living in caves and, as I say, freezing to death. The other school says, no, we've got lots of stuff to burn yet, thanks to fracking and all these other techniques. But we're going to put so much greenhouse gases into the atmosphere that we're going to cook. You can take your choice of human's fate between freezing and cooking. I personally think that cooking is a more likely outcome. So as humans, we're going to have to do something about these cliffs. We're going to both have to find ways of creating energy that don't put out pollution, especially greenhouse gases. And we're also going to have to find ways of using energy more effectively. Conservation and the way we live and so on. Today we're going to talk about one of the ways you can produce energy without creating greenhouse gases. And that's, of course, nuclear energy. We already get about 20% of our electric energy and about 7 or 8% of our total energy from nuclear, so we know how to do it. And it's worth just going back a little bit into the history of how nuclear energy came about. Probably the most important thing to remember is 1905, when Albert Einstein issued a series of amazing papers, one of which told us that mass and energy were essentially the same thing, and that you could actually go from mass to energy, in theory at least, and back. And how much energy you got as a result of converting mass to pure energy, and in contrast to burning it, was determined by the most famous formula in science, E equals mc squared. And when you convert mass to pure energy, it goes away. Unlike burning it, all we're doing when we burn something is we're converting a liquid, like the gas in our car or a lump of coal or whatever, to gases. We don't violate the rule that matter can't be created or destroyed. But when we convert matter to pure energy, it does go away, it becomes energy. And we get to multiply it by c squared in the formula. And when you put in actual quantities, c squared ends up as a number with about 20 zeros. When a good share of the world's great scientists physicists, the physical chemists gathered in Los Alamos to build the atomic bomb in the 40s, they were given a set of briefing papers, which kind of explained what we knew so far about how to build a weapon and some of the basics that they could deal with. Obviously, these were highly complicated papers because of the nature of the audience. They were jokingly called the Los Alamos Primer, based on the kind of things you read in grade school, but of course they were full of all these complicated formulas. One of the things that was calculated in there was the difference between how much energy you got when you burned an ounce of something versus the amount of energy you got if you converted it to pure energy. And the difference comes out, in theory, to 10 to the 7th, or about 10 million times. We don't get all of that in the systems that we have now, but we get quite a bit. You can illustrate that, and I forgot my raisin. I use a raisin because the calculations have been done on it. But if I burn a raisin, I can get some energy. It's got some carbon, hydrogen in there. If I convert a raisin to pure energy, I can get enough energy to run the Twin Cities area for about 10 days. Transportation, machines, heating buildings, elevators, whatever. This really came to the fore in the late 30s. And in the late 30s, attempts were being made to alter the nucleus of the atom to see if it could be changed into something else. What something is depends on how many protons are in the nucleus. We have, and you can start to look here now at the first page of your handout, there are 92, in the Earth at least, natural elements. They range from the lightest, hydrogen has 1 proton in its nucleus, all the way up to 92 in uranium, which is the heaviest. Tin has 40, helium 2, and so on. And you see examples there of atoms, which comprise everything. You, the chair, the building, and so on. The atom has a nucleus, which has practically all of its mass, and that's surrounded by electrons in rather weird orbits. Okay. The nucleus, these are the white guys with the plus, they have a positive electric charge. The neutrons, as the name implies, the black ones, they don't have an electric charge. And then for every positive proton in the nucleus, you've got a negative electron circling in these weird orbits that you see there. They're kind of like little solar systems. Now, we all know from our science that like charges don't like each other. Positive electric charges repel each other. Negative charges do the same. The closer they are together, the stronger are those forces that repel. Nothing is as close as the particles in a nucleus. As a result, every nucleus on Earth should explode. We should explode. Everything should become cosmic dust. They should explode. Well, they don't. And this is the key thing if you don't learn anything else from today. They don't explode because a tiny bit of the mass in every nucleus gets converted to pure energy. And that's the binding energy that keeps every nucleus from coming apart. And that's the strong nuclear force that's holding those things together. And what scientists were trying to do in the 30s was see if the proton content of the nucleus could be altered and change one element into another. Because if you could subtract a proton from an element's nucleus, it would become one lighter on the element scale, and so on. And the way they were trying to do that, and they were using uranium, the heaviest element, which they thought would be the easiest to cause to change, they were bombarding it with neutrons, the black guys. They didn't have an electric charge. So this positive nucleus would accept the neutral neutron, and they hoped something would happen. And what was happening was, one, this nucleus would discharge some some protons as a result of that, and the number discharged would typically be 2, which we call alpha radiation. So when it did that, let's say it's uranium with 92, it discharged two protons, and now it has 90, and that's a different element. That happens to be thorium. The other thing that amazingly was happening is the white guys, the neutrons. In the white guys, one or more of them would change into a proton. It would literally become a positively charged proton and make the element one step heavier. Now, if that happens to uranium, which is the heaviest element, you would create artificial elements beyond the 92. And that's what was happening in Italy when Enrico Fermi was running his experiments. And he started to create some additional artificial elements. They were using solar system names, so uranium then, if it got one more proton, became Neptunium. And if it got a second proton, it had 94 protons now, and that was plutonium. Fermi gets the Nobel Prize for his work in, I think, 1938, and Mussolini lets him go to Stockholm to get his prize. I guess he expected the money to be handed back when he got back, but Fermi wisely escaped from Stockholm to the United States, where he subsequently played a major role in the Manhattan Project. He and Leo Szilard built the first chain reaction pile in the squash court at the University of Chicago, and he went on to become probably the most important figure, technical figure, in the building of the nuclear bomb in the Manhattan Project. Many other European scientists escaped at the same time. Hitler didn't like communists, he didn't like Jews, he didn't like homosexuals, etc., etc. Well, in that whole list, you had a good share of the better physicists in Europe, and many of them did end up in England and the U.S. and were, of course, key persons in the building of the atomic bomb and the subsequent use of nuclear energy. Now, the other experiment besides Fermi in Italy going on was in Germany at the Kaiser Wilhelm Institute under Otto Hahn. Otto Hahn had a very important assistant, a woman physicist named Lisa Meitner. She was Austrian. Hitler takes over Austria. Her position becomes very precarious, and so she flees and gets to Stockholm. That trip would have made a good Hitchcock movie, but she gets there anyway, and continues to communicate with her colleagues in Berlin. They're doing the same thing that Fermi is. It's in your second picture here, and that big ball with the white and black guys, that's a uranium nucleus, and they're hitting that, or they're sending in neutrons, and some of which get captured by that nucleus and cause the nucleus to do things. And they're looking for neptunium and plutonium, and they're also looking for lighter elements like thorium that are close to uranium. But the amazing thing for them is they're getting barium. Barium has 56 protons, and they can't figure out how something with 92 protons could suddenly drop down to 56. They're not detecting that kind of radiation. Well, in Sweden, Lisa Meitner figures out what's happening. And she figures out that this nucleus, this heavy uranium nucleus, isn't just changing one or two spaces up or down. It's literally coming apart into two smaller elements, and that's what you see happening in your little drawing. So, and one, of course, is barium, and the other would have to have 56 from that, would have to have 36 protons, and that would be krypton. And sure enough, she sends all this data to her buddies in Berlin, and sure enough, they find krypton and realize what is happening. A paper gets published in a key London journal. There's complications in Lisa Meitner sending her data to Berlin and vice versa, and her name and contribution doesn't get in the first paper that's published. That paper electrifies, if I can use the term, the whole world of physics, especially in the US. And the thing that they realize, and that she has in her calculations, and I'm oversimplifying this, but what's happening? Sorry, what's happening is that each of these two smaller elements are also converting a little mass, so they won't fly apart, right? But the total mass that you need to convert in the two smaller ones is less than the one you need in the big uranium one. There's a little bit of mass to energy left over. If you don't remember anything else, that's the key. That's left over. And that's released in heat and light energy. And she calculates how much that is. And in the US, one of the fugitive physicists, Leo Szilard, sits down, I guess he sat down, and he does a quick calculation. And he realizes how much that energy is, and that neutrons, extra ones, you see some black guys are taking off there, and if one of those finds another uranium nucleus and makes it come apart, that releases energy, and some more neutrons, and that'll find one, and so on, and you'll have a chain reaction, okay? And he calculates, he also figures out if you have enough of good fissionable uranium in the right density, that more than one of these neutrons will find a nucleus. So instead of a one-for-one reaction, it'll go up geometrically. In one of these little fuel pellets, in any 1 second, 50,000 uranium nuclei will fission. And it'll make 50,000 more fission, and another 50,000, another 50,000. So you have a controlled chain reaction. But if two neutrons find pellet or nuclei to fission, 50,000 will make 100,000, and 100,000 will make 200,000, and so on. And Szilard calculates that in 1 microsecond, you get 80 of these generations. He didn't have one of our modern calculators, but he was a pretty smart guy, and he could quickly figure out that 2 to the 80th power is a really big number. And Szilard sits down and he literally designs a nuclear bomb on the spot. And even at the moment he's in England, then he sends for the US, and in each place he applies for a patent on this nuclear bomb. He becomes a key part of the Manhattan Project, and is continually demanding royalties from the US for his discovery, which they ignore. And Szilard does, though, perform an important function. He is very worried about the Germans realizing that neutrons are released. That isn't in the first paper. And he wants to make sure everything's secret, and also that the US get going on his bomb before the Germans do. And he writes a letter to FDR describing as best he could, you know, what could happen, what kind of a weapon you could make. And he realizes that he's just some guy, some weird physicist there at Columbia, and FDR is not going to pay attention to him out of the thousands of letters he gets. He goes to Fermi, who by this time is at Princeton. Fermi validates his work and realizes that he may have a problem. They often find Einstein. And Einstein signs Szilard's letter, and Einstein is working with he knows a big Wall Street guy that sees FDR every day. The Wall Street guy carries the letter into FDR, and FDR starts the Manhattan Project, which is the largest industrial project the world had ever undertaken up to that time. It ends up in Los Alamos, and the rest is kind of history. So what's happening then, coming back to our key experiment here, is that we're making these uranium nuclei come apart, and we're releasing this energy because there's some mass to energy left over with this huge multiplier that EMC square tells us. And as the Manhattan Project matured, the bombs go off, and Navy Admiral named Rickover decides boy, this is the way to solve the eons-long program how to fuel nuclear vessels, especially submarines. And he assembles a crew, and they design a small reactor, nuclear engine, that can go on a ship, specifically on a submarine. And the Nautilus submarine takes one of these reactors. It's about a 50 megawatt capacity reactor. That would compare to like 1,000 megawatts for a big operation down here at Prairie Island. And the submarine Nautilus, using only its new nuclear reactor, goes 2,000 miles under the Arctic ice cap. And that, of course, sets off an understanding of how reliable and effective nuclear power could be. And most of our current commercial reactors are essentially large versions of that Rickover design. And that history is reversing itself because probably the biggest thrust right now in nuclear energy is to go back to smaller modular reactors. And the Department of Energy, Tennessee Valley Authority, and others are putting a bundle of money into essentially marine vessel type reactors that could be modular and assembled almost like on an assembly line and put in more simply than the current very expensive reactors. An operation like Minnesota Power up in Duluth gets most of its energy from coal and is under huge pressure to do something. They can't afford a $5 billion version of what's at Prairie Island. So, but these nuclear reactors, a couple of these smaller ones would only cost them a couple $100 million, and they might actually substitute for a lot of the coal they use. So if there's a trend in nuclear power right now, that's one of the big ones. If you turn the page, you can see how a nuclear reactor works. What happens is uranium is in the ground. It's in very low concentrations. You dig it up just like any other metal ore, crush it, use the magnets. Luckily, uranium is very heavy, so magnets will pull it out. You refine it, and you end up with uranium. It's in the form of uranium oxide. It's called normally yellow cake, a term you may have heard, and that's basically uranium. And there are two versions of uranium in the ground. I've mentioned that what something is depends on how many protons are in the nucleus. An element can have a number of different versions with more or less neutrons. It doesn't affect what element they are, but they're different, what's called isotopes. Okay? Uranium comes in the ground in two isotopes. Uranium 238, the heaviest one with a few more neutrons, and uranium 235. Back in the Lisa Meitner days, when they were doing those experiments, they were hitting just uranium and had both 238 and 235 in it. 99% of the uranium is uranium 238 that doesn't fission. And she realized that what was happening, they were getting the barium from this less than 1% 235. It turns out to make an effective fuel pellet that will keep the chain reaction going, it needs to be about 4% of the good stuff, the 235 that fissions. So once we get the uranium out of the ground and we've refined it and got it there, we have to enrich it. And the way we do it now is whirl the stuff around, we gasify it, throw it around in centrifuges. The lighter good stuff, slightly lighter, stays in the center, and the heavier stuff we don't want goes out to the outside. Not much of a change one time. We pull out the slightly more good stuff from the center, send it into another centrifuge, and whirl it around again. In order to get it up to 4%, you need several hundred of these centrifuges. But we do that. And you can also do it as they originally did, going through filters, which takes much more energy, and that approach is pretty much obsolete. When we get to 4%, we make them into ceramic pellets. They go into, and on the next page you can see the long cylinders are about the width of a golf club shaft, and you stack up these pellets in there to put them in the reactor. Okay. The interesting thing here to note, you see these two workers with no protective clothing. Those are new fuel cylinders that are going to go into the reactor. They've got thousands of radioactive uranium pellets in them, and they don't need any protective clothing. The reason is uranium has a long half-life and isn't very radioactive. In addition to that, the radioactive it emits is easily blocked by the outer skin. I can put a dish of, these of course are just replicas, they're not actually uranium pellets. They just look like them. But I could put a dish of uranium out here and it wouldn't hurt you. You wouldn't want to swallow one, that wouldn't be a good idea. But they're ceramic, so you couldn't chew it. But anyway, so they're in those. And what happens is, once we've got the pellets, we've got the stuff up to 4%, we put them in these cylinders, and you see it up at the top here, these fuel assemblies, and they go in they're the reactor. And you see the design of a typical pressurized water reactor here. The pink thing on the left, that's the furnace, the nuclear furnace. And what's happening in this pellet is that all these things are fissioning, they're releasing heat, and this thing gets hot, 4,000 or 5,000 degrees or so. We pump millions of gallons of water through here and we heat it up. And it's just like any other power plant. We got hot water, and we'll use the hot water and we'll make steam. And not to get too far off the track here, another thing that the water does, in order for this, coming back, one reason I don't use PowerPoint is it's so easy to flip pages here rather than going through these stupid slides. My geek sons keep wanting me to put all this stuff on PowerPoint, but I've resisted it. Anyway, where was I? So, I've got my things, water is flowing through, and as you see, we aren't going into great detail, but essentially we make the power plant. We make steam. The steam drives a steam turbine, it turns a generator, and we make electricity. The other thing is that the water does, to get these nuclei to accept this, to catch this neutron, which is the whole thing, the reason the thing works, we have to slow them down. When they leave here, when these neutrons fly out, they would circle the Earth in about 1 second. But we got water there, and these things hit the water, they hit the protons, the hydrogen in the water, they slow down, and they slow down enough. That makes practically all of our reactors inherently safe. The biggest danger, and we saw it in Japan, you lose power and you lose your water supply, you can't cool things down. This reactor, the pink thing, pink guy, that water in the reactor, they're at about 600 Fahrenheit, and that's the cooling that's going on. So if we lose water, that's not so good. But if we lose water, the neutrons speed up, they quit getting captured, and the reactor shuts down. It's what's called a negative void coefficient. The problem at Chernobyl, the Russians were using a military reactor. It wasn't using water for that, it was using graphite. And that had what's called a positive void coefficient. If they lost whatever water they had, the thing would actually speed up. And that's what happened there. There's a lot more to it than that. Next week we'll say a little more about that. The thing speeded up, overheated, created steam and hydrogen, and they had a steam hydrogen explosion, the same sort of explosions that occurred in Japan. They did not have a containment building, which our reactors have, blew the roof off, blew all that graphite all over the place, and became the largest dirty bomb in history. It wasn't a nuclear explosion, but it blew radioactive material all over. You see above the Prairie Island Nuclear Plant in Minnesota, a place I like to take classes to. It's an excellent place to visit. You see the two containment buildings. There are two reactors there. The biggest problem with nuclear, of course, is what do you do with these pellets? We start with 4% fissionable uranium in here. The fact that 96% of it is the 238 that doesn't fission helps us control this into a one-to-one reaction. If this now had 90% fissionable stuff, that's when the reaction would go up geometrically. And instead of running the elevators and keeping the lights on, this pellet would blow up the city. Right? But in order to do that, it has to have a high concentration. The fact that it only has 4% prevents that from happening. The other thing that happens in this pellet, remember I said some of these neutrons could become protons. A little bit of this 238, the 96%, has that happen. And about 1% of it becomes plutonium in all of our reactors. So now we've got and the plutonium fissions, that's good fuel, like the 235. So we end up with about 5% good stuff in here. And this continues to fission and stay hot for about 5 years. Even though thousands of them are going away every second. The number of atoms in here is probably a number with 23 zeros or something like that. So after about 5 years, the amount of good stuff drops to about 2%. And it won't sustain the reaction anymore. And it is now spent fuel or nuclear waste, depending on your point of view. If you're a nuclear advocate like me, you'll call it nuclear. You'll call it spent fuel. If you're not, you'll call it nuclear waste. The stuff it makes, I think I included it in here. Yes, I have. If you'll find this drawing on the bottom of the one showing the reactor and the pellets, you'll see the content of this pellet. This is helps you. You've got 4% uranium-235, and you've got the rest uranium-238. But from the 238, we're going to make some plutonium, right? And it's the plutonium, you'll see it there in the middle, and the 235 that break into smaller elements, like you saw on the front page. Those are fission products. Those are like the barium and so on that it broke into, and there's cesium and strontium and all these things. Those are radioactive and can be quite dangerous. In your handout, it shows some of the different fission products. The really dangerous ones are the ones that deteriorate or radiate at a middle level time scale. They have what's called a half-life of about 30 years, which means in a particular hunk of it, half of it will be gone in 30 years. Uranium's not very radioactive because 238 has a half-life of 4.5 billion years. That means that, since that's about the age of the Earth, that means that about half of all the 238 that was here when the Earth is formed is still here. Uranium-235, the good stuff, when the Earth was formed, there was quite a lot of it here. But it goes away faster. It has a half-life of 700 million years. So it's down to less than 1% of the uranium we have. I'm not sure I'm making sense. But over here on the left, then, is the stuff that is a problem in this thing after 5 years. The rest of it is either mostly this 238. There's a little good fuel yet. There's the 2% that's not enough to sustain the thing. What the French do is they chop these pellets up. They separate the bad stuff, the radioactive fission products. They vitrify them into glass cylinders, and they put them in the floor of 2 or 3 rooms, large rooms, at La Hague, where they do that processing. All the rest of the spent fuel gets recycled. Okay. We don't do that. We take the whole rack, those racks you see that have now been in there for 5 years, we take them out and we store them. We put them in either a pool, big pool, well, we put them in a big pool of water at the reactor, and they sit there in the reactor, in the pool, for about 5 years, slowly cooling down the radioactivity. They're still radioactive. After about 5 years, there's no more room for them. They take them out and put them in big concrete and steel casks. And you see the picture of at Prairie Island, and it shows that big concrete pad there out in front, and those casks are all sitting there, okay, with those radioactive spent fuel pellets in them. Nobody knows how long those casks will last before they might start leaking radiation. The big plan was to take those casks and put them in a geologic storage site. Years ago, a big study was done, and Yucca Mountain, Nevada, which is a big mountain ridge, was chosen. Every nuclear power plant, all of these, has to send in 1/10 of a penny per kilowatt hour into a geologic fund. Nuclear plants put out 800 billion kilowatt hours a year in the U.S., and that fund is now well over $20 billion, 25 billion or something. Half of that money has been spent on a very elaborate storage site in Yucca Mountain, Nevada, where those casks, in my opinion, should be sent. But they're held out. The Nevada political parties are refusing to allow the thing to go, to continue forward. The Obama administration has agreed with this and has cut the funding at Yucca Mountain, even though the thing is essentially finished. In addition to that, they're actually starting to dismantle it. There's a report from the General Accounting Office that says the reason the thing was shut down was political, not scientific. You can argue both sides of the issue. I was thrown off the DFL Central Committee for writing an editorial saying that Obama had made a huge error in canceling it. So that's my opinion, but it's only me. I've never even been there. Anyway, so at about 70 locations around the country, these casks are sitting there. No one say in 100 years or more, they can start leaking radiation. After about 300 years, most of the danger from these used pellets is gone. There is still material in there that's radioactive for an indefinite period, but the longer something is radioactive, the less radioactivity it emits. The really dangerous ones have the short half-life. You're really getting a lot of radiation from them. The really short ones, and they're shown in your handout, go away pretty quickly in months or years. The most dangerous ones are things like cesium and strontium that are about 30 years. That means they're going to be it's going to be quite a few hundred years before nearly all of the stuff has decayed into something else. So here we are. We've got these plants. They're all cranking out electric power, and they're doing it because Lisa Meitner initially figured out what was going on. Her recognition, however, did come later. These artificial elements have been named, that have been created with more than 92 protons are named for things. There's californium and so on. I think there's an Einsteinium, and one is actually named Meitnerium for Lisa, who the whole world now finally realizes what happened. But then you could say the fate of women usually is that they do the work and men get the credit, right? Well, she was a perfect example of that in the late 30s and early 40s. I mentioned how the carbon dioxide issue, which is a big one, one of your charts shows the various fuels and the relative CO2 emissions from them, and obviously nuclear plants emit water vapor. There are some diesel-driven pumps and generators and things of that sort. So there's some emissions from a nuclear plant, but they're relatively small. Gas is about half of coal. Again, coal is basically all carbon, and the pressure right now is on to reduce coal. Coal, up until the last couple of years, was about 50% of our electric energy. It is now down to, in the mid-30s. So the EPA and others are forcing coal plants to control their emissions, which is very expensive, but can be done. You can put scrubbers and things on to limit the sulfur and mercury emissions, which are serious hazards. There isn't anything you can really do about carbon dioxide. Carbon dioxide is inherent in burning. When you burn coal, you make carbon dioxide, and it goes up the stack. Our biggest power plant is the Sherco plant up the river at Big Lake, 50, 60 miles up the river. It's a 2,100 megawatt plant. It's the largest plant in Xcel Energy's fleet. It burns about, I think, 5 or 6 million tons of coal a year. Every day at Sherco, there are 2 or 3 100-car trainloads of coal that roll up to that plant. Coal gets crushed. There are 3 20-story boilers there. That coal gets burned, 50,000 tons a day or whatever it is. And there are 2 giant smokestacks. And about, I think it's around 15 or 16 billion, wait a minute, 5, 6 million tons, sorry. 15 or 16 million tons of CO2 go up those 2 stacks every year. In your car, out in the parking lot, when you burn gasoline, if you go 10, 12,000 miles a year, you emit about 5 tons of CO2 out your 5 tons of CO2 out your tailpipe every year. So if you don't like CO2, get a bicycle, right? So anyway, the pressures on coal. Older coal plants are simply being retired. The main way they're being replaced right now is with natural gas. And a good example is the end of Randolph Street in St. Paul, down at the river. You see the old coal plant that is no longer operating on the south side of Randolph, and on the north side you see a newish combined cycle natural gas plant, which has replaced it. The same thing has occurred over in Minneapolis, the Riverside plant. So that's going on. Coal here in the U.S. consumption is mainly for electric energy. It's declining. But in the rest of the world, it's not. India, China, Indonesia, those countries, they've got coal, and they're growing rapidly, and that's what they got. So their use is going up. So the world, I didn't bring a lot of data about this forecast. We don't have that much time. But the world use of coal is rising. The scheme is to do something called carbon capture and sequestration at the stack, and somehow try to separate, which can be done technically, the CO2, but it's just not a workable process. And so the climate cliff is there, and part of it is a result of, say, of coal burning, which worldwide is actually increasing, and in all the forecasts is projected to continue to increase. The Chinese and India, their main answer is nuclear. They are the response, or the approach now to nuclear power varies greatly. You've got Germany and Japan, Italy, Switzerland are saying no more nuclear. And Germany's actually shut down half of its nuclear plants. Japan had 50, 4 were clobbered by the tsunami, and all others were shut down. That, however, creates a huge problem, and what are you going to do? What Japan is doing is importing natural gas. They have a major conservation program. I think the Japanese are more compliant than we would be about using less energy. But they're stuck, and they've started up 2 plants, and the battle is on in Germany and Japan whether or not they will have to reopen more of their nuclear plants. They work fine if they're not hit by a 50-foot tsunami. And Germany at the same battle between the very strong green parties and the people and the business people who are having to pay a lot more for their energy. The Japanese are paying about 4 times as much for natural gas as we do, importing the liquefied stuff that has to be shipped over there. An interesting thing that happened this past month, a nuclear-powered Russian icebreaker escorted a ship full of liquefied natural gas from Norway across the North Pole area to Japan. That cuts the sea passage almost in half. Otherwise, they have to go down through the Panama Canal or over through the Suez Canal. And it looks like, and in the summer, last summer, that part of that passage was pretty much open. So it looks like we're going to be seeing Europe to Asia travel through the Arctic area, the fabled Northwest Passage, will be at least part of the year open. The Arctic ice cap is steadily shrinking year by year, one of the examples of what's happening with global warming. I put on here one illustration about nuclear radiation, which will be a subject that will come next week. What we've got here are columns. The left-hand in doses in rems, which is the unit that we usually use, and typically we use a millirem or 1,000th of a rem. And you start here with 1 through 10, and then 10 through, and so as you go over to the right, you get higher and higher doses. All of us, on average, from cosmic rays, we breathe radon, which is around. Uranium decays into radon. Uranium and thorium are in the ground almost everywhere in small amounts. We go to the doctor and we get x-rays, we go to the dentist, and so on. We take airplane flights, and the higher you are, the more radiation you get. If you live in Denver or whatever, you'll get more cosmic rays than if you lived at sea level. And the average person in the world, including the US, gets about 1/3 of a rem every year from natural sources. And it's fair to say, I think it doesn't hurt us. Otherwise, because that's been going on since humans were on Earth, and we're still here. One argument is that, and that's pretty well justified, is that small amounts of radiation do something to the body, to the DNA, but the body fixes it. And that up to a certain point, we are not hurt by radiation. We get, as I say, the average person gets 300 millirems, or about 1/3 of a rem every year. Persons who work in the nuclear industry that are close to sources of radiation are allowed to have about 15 times that much radiation, or about 5 rems per year. As I'm not sure this is shown here, but yeah, kind of on the right-hand side where you start looking at a lot of remember the thousandths or 1,000th of a rem. As you get 100 times normal radiation, 30, 40, 50 rems, good chance you'll get sick, probably recover. If you get 300 or 400 rems in a short time, you're likely to die. So it's like, it's a little like vaccines, I think. If we're going to protect you against a disease, we inject you with small amounts of the stuff over a period of time, and your body builds up antibodies. So when more of it comes along, your body can deal with it. But if you get too much, it overwhelms the defenses. So in the range of hundreds of rems, that will overwhelm the defenses. At Chernobyl, the initial explosion killed, I think, 30 or 31 people. The Russians didn't seem to care. They just sent rescue workers into the plant to do things. Another 30 or 31 or 2 got lethal doses of radiation, and they died. There was a kind of a famous period there where one American physician I know was trying to do bone transplants or whatever to see if you could save some of them. I don't think it worked very well. All kinds of stuff, radioactive material went out, one of which was iodine-131, which causes thyroid cancer. You may have heard during the Japanese issue, they were issuing thyroid pills, and what those do is prevent the thyroid from absorbing this radiation. Russians didn't do that. The 131 got in the grass. The cows ate the grass, and they gave radioactive milk. About 5,000 very young infants, especially, are very susceptible in the Kiev area, got thyroid cancer. And from the last I've seen, I try to look at these reports, 15 or 16 of them died. Most of them were cured. So the known deaths at Chernobyl from nuclear radiation or whatever is in the range of 75 or 76. A huge cloud of radioactive material went west and north as far as Scandinavia. Hundreds of millions of people were living under the cloud. It's possible that cancer rates went up in areas over which that cloud went, but studies have not been able to identify any. It's just very difficult. In Japan, quite a lot of radiation was emitted. An area, a 13-mile radius from those 4 reactors was evacuated, about 100,000 some people. And based on the levels of radiation there. The Japanese also sent in people to try to deal with the damage, but they were careful as to the time and the protective clothing and so on. At this point, there's no evidence that anyone has gotten either sick or died from radiation in Japan, due in large part to the fact that the Japanese are very carefully monitoring things. Some parts of that 13-mile radiation have been deemed safe. The levels they're using as to what's safe are the kind of levels that we use now for nuclear workers. And they're based primarily on people who are there in the daytime. Again, it's assumed that nuclear workers are not going to spend 24 hours next to these machines that may be radioactive. So in quite a few of those evacuated areas in Japan, people are being allowed to go back in the daytime. A couple of villages have been opened for all the time, but most of that 13-mile radius is still, they're still not permitted to go in 24 hours a day. Radiation gradually dissipates, and at some point they'll reoccupy that area. There are large areas around Chernobyl that are still evacuated. There are disputes about whether they could be used or not. And I'll have a little more data on that if you come next week. But since 3 Mile Island, our nuclear plant activity pretty much quit.